Today we'll look into graphing trigonometric functions, specifically sine and cosine. But to do that, we're going to first look at how we normally graph linear functions. So back in, I don't know, 7th grade, whatever, you had this function, and we set up a table where you have x's and y values, and the y values you got by plugging the x's in. So I've displayed those right here, and then we went and just, found all those points, and drew the graph, etc., 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 and we're done. No different for sine and cosine values, except we don't get sine and cosine values easily necessarily from a table. We get them from easily the unit circle. So what I'm going to do is I'm going to take a look at my easiest possible values for the sine of theta. And remember, the sine of theta, since this is a unit circle, is our y values. So the easiest ones I get are when I'm at 0, pi over 2, pi, 3 pi over 2, and 2 pi. And the reason why I say they're easy is because they're either ones or zeros. So the y value at 0, which is here, is 0. The y value at pi over 2 is 1. Y value at pi is 0. Y value at 3 pi over 2, negative 1. And the y value at 2 pi, 0. Put a 1 here, negative 1 here. And we draw a relative facsimile of a sine graph. Likewise, cosine can be done the same way and take values at 0, pi over 2, pi, 3 pi over 2, and 2 pi, and graph the cosine values, which in this case are x values. So at 0, my x value is 1. Pi over 2, it's 0. Pi, negative 1. 3 pi over 2, 0. And 2 pi, 1. And I connect the dots. And I'm doing it in this curvy linear format because that's what it actually looks like. It's not linear. And go from there, and there's our relative cosine value. Now, some special notations about these kind of trigonometric functions are here. Okay, so when I have a graph that is, somewhat symmetric between the high and the low point, not symmetric per se, but it gets cut in half, that halfway point between the highest point and the lowest point is called the midline, which is not necessarily written in the graph itself, but you can find that by taking the difference of the high and the low and dividing by 2. From the midline to the high or to the low itself is called the amplitude. So in this case, we have an amplitude of 4, and it's 4 here and 4 here. Amplitude is a relative absolute value, if you might. In terms of these spacings where either you have an intercept or a high point or a low point, all right, we call those guys intervals. So this is spaced in 90-degree intervals, just like I did on my sine and cosine graph, basically where we get those zeros and one spots or some critical values, all right? And these can be either in degrees or they can be in radian values. And then the time it takes for the graph to repeat itself. So notice up, down, up, and here I go repeating itself, is called the period. All right. And notice I can go from this point here and to this point here, and then it repeats itself. That's also a period. And you'll notice the period is 360 degrees, or 2 pi in this case. And if I go from 90 to 270, that's also 360. And negative pi, that should be over 2, sorry, to 3 pi over 2 is 2 pi. All right, so those are some important conversation pieces, definitions about these graphs. Now, every sine and cosine graph can be moved around just like our parent functions were. And the general formulas are as follows, and this is the equation and the way you want to represent it. So you have some A, which is going to be your amplitude, is equal to K times X minus what we call a phase shift, and we'll talk about that in a minute, plus H. All right, now the H and the K are a little bit different here than you're used to be notating. So K talks about a period change, not the exact period. It turns out that K is a divisor of an actual period for sine and cosine. So for sine and cosine, we know our period is 2 pi. Whatever that K value is, if you divide 2 pi by it, you'll get the period of your graph. All right? And we will talk about phase shifts and this H value as we move along. So if I were to graph y equals sine of x, I'm going to just go ahead and I'll do it in degrees just for a change. We already graphed one of these, and we said sine of x looks like this. Oops, this goes down to here, back up to here. So here's sine of x. Now, intuitively, this has always been our a value in front of a function, and this is actually our amplitude value, which is equal to 3. So that means that's the absolute value of the distance from the midline, and this 0 is the midline. So now if I go up to 3 high, actually let's do that in green, and -3 low, that's where my new graph is going to go to. The y values for each of these are going to be multiplied by 3. When I multiply 0 by 3, I get 0. 1 by 3, I get 3. -1 by 3, I get -3. So this is my green graph for sine of x. Let's go black. For -4 sine of x, I'm going to multiply all my y values by a -4. So I take and multiply 0 by -4. I get 0. 1 by -4, I get -4. Notice what's happening here. 0 by -4, 0. -1 by 4, I get 4. And 0 by -4 again. So notice what this did. It basically reflected the graph and changed my y values by a multiple of -4. So now we're taking a look at what happens to this value in front of the x, or in front of the theta value. And if you look back at our previous slide, we're talking about this k value right here that's changing because that's in front of the x value or the theta value, whatever you want to call it. So cosine of x, here's my 1, and here's my -1. And let's do these in terms of degrees to start with. We'll use other stuff later. Okay, so this here is 0, 90, 180, 270, 360. All right, so what's going to happen here is that we still have our cosine graph as usual. And it looks something like this. Now, what's going to happen in our next graph, notice this k value is not the period of the graph. Okay, the k value is basically an x multiplier, all right? But in order to make it look like the x multiplier of times past, all right, we would really have to write this as, you know, the cosine theta over 3. But we now know that the period is equal to 360 over 3, or 120. Now you'll notice every one of our graphs up to this point has had basically 4 spaces in them. All right, here's 1, 2, 3, 4 spaces. Those 4 spaces basically notate the 4 quadrants that the circle goes through. So for a period of sine and cosine, it's going to go through 4 quadrants before it starts repeating. However, these 4 quadrants are going to happen in 120 degrees now, which doesn't really make sense, but these spaces are going to compress. We know that we have a division of 3 for each x interval. So what I do in this case is I know my first 90 degrees interval is going to compress to 30. My next 180 is going to be 60, then 90, and then 120. So another way I get that interval is I take my period, divide it by 4 to get my interval. And my period in this case is 120. Dividing it by 4 gives me 30 degrees. So now my x value, you'll see where I came up with those numbers that I just talked about to you. Except I think finding your new period and then dividing by 4 for sine and cosine get those numbers a little bit easier. My y values are not changing. So my graph looks exactly the same, except my x values have changed. Now this is a little bit deceiving because when you stack them on top of each other, the graphs look identical. It's just your x values have changed. So in theory, this graph right here happens in 120 degrees, which let's say is ish right here. So this will go something of this effect. Let's see, how am I going to do this? Something like this, like so. In other words, 3 of these will now happen in 360 degrees because at 120 degrees, that's where one period ends. So I'll have 3 periods of the graph within 360. This part of the graph right here, it takes 120 to happen, but this is what we call a cycle of the graph. A cycle is just a snapshot of one period and what it looks like. All right. Now in this case, we know that our k value is a half. So if the period equals 360 over k, that's 360 over a half, or 720. My intervals are 720 over 4. So in this case, my period has basically doubled, and so are my normal intervals. My intervals are going to be 180. So 0, 180, 360. Add 180 to that, that's 540, and 720. And again, there's no change in the y values, so my graph looks exactly the same. Up to this point, we have used 360 as our notated period, and we're going to change that now because we're using a radian value for our k value. So we know our k is pi, and now we can say that our true period is 2 pi over that k value of pi, so our period's 2. The interval calculation doesn't change. It's equal to your period, which is 2 over 4, which in this case is a half. So I start at 0, as I normally did, and go by halves. And you'll notice I end up at the number 2. All right, my period was actually 2, and that's what I'm showing right here. Again, my y values haven't changed, so my cosine still looks as it has throughout the entire set of problems. And here's a little pictorial of what all three look like stacked upon each other. You'll see that in this orange graph, the cycle, there are 1, 2, and 3 cycles in 360 degrees. All right. In 720 degrees, only 1 cycle exists, while in regular cosine, there are 2 cycles within the 720. All right. You'll notice that if I compare it to the 360, only half of a cosine cycle appears there, where 3 cycles of the cosine of 3x shows. So now we're going to combine both of these. Notice my a value, which is like my y multiplier, is 3, and my k value is a half. So what I know is I know that my 1 is going to change to a 3, and my negative 1 is going to change to a negative 3. My period is, let's just do it in terms of pi, 2 pi over a half. So my period is 4 pi, and my interval is 4 pi over 4, or pi. So notice I go from 0 to pi to 2 pi to 3 pi and to 4 pi. And what I'm going to get is I'm going to get one sine function within there. So at 0, which is my normal sine value, I multiply that by 3, I get 0. At 1, which is my normal sine value, I now get 3. At 0, I multiply by 3, I get 0. At 3 pi, which would be my normal negative 1 value, I get negative 3. And at 4 pi, I get 0 again. And here is my graph. It looks just like a sine graph, but notice both my x intervals and my y max and mins have changed. Again, we'll change this here. I have an a value of 5 actually with a flip. So my a multiplier is negative 5, and my k value is pi over 2, so my period is 2 pi over 2, which is 4, which makes my intervals 4 over 4, or 1. So I'll do my intervals first. 0, 1, 2, 3, 4. I will change my values from 1 to 5 and negative 5. My normal value for cosine is 1, but I'm multiplying that by negative 5, so I'm down here. That's where that flip comes in. Then I go to 0, up to 5, because I'm multiplying my normal negative 1 by a negative 5, back to 0, and back to negative 5. And I get a graph that looks just like a cosine graph, but the y and the x values have changed. So now we're going to take a look at this piece of the graph, all right? And this is actually my phase shift portion of the graph. Now what a phase shift does is it moves things to the left and to the right. So if I'm going to do that, you'll notice that in this general equation that I wrote, it looks a lot like y equals AF of x minus h over b plus k. All right, and this value is whatever comes after the negative sign. So let's go back to our example. And in this case, you'll see pi over 2 is represented here. This is our phase shift. I'm going to go PS for phase shift. So since it's after the subtraction, that means this graph moves pi over 2 to the right. So here's what I tend to do. I know my period in this case is not changed. It's equal to 2 pi. My intervals are 2 pi over 4, or pi over 2. But I'm sliding everything to the right pi over 2. So normally I would be at 0 here. Well, now I'm going to change and slide everything pi over 2 to the right. So this 0 gets adjusted to pi over 2. And then since my intervals are pi over 2, I keep numbering by pi over 2. So pi over 2 and pi over 2 is 2 pi over 2, which is pi. Then I have 3 pi over 2, 4 pi over 2, which is 2 pi, and then 5 pi over 2. Now notice, from pi over 2 to 5 pi over 2 is 4 pi over 2, which is 2 pi, and there's my period of sine. No change in the y values, but these are my new x's. So if there's no changes in the y values, then my normal sine graph is just going to pop up again. Here's my 1, here's my -1, and there's my graph. Same thing happens here, period 2 pi, and I know I have intervals of pi over 2, and now I'm moving backwards. My phase shift is negative pi over 3, like so. Notice, I've got an issue here. It's not like last time where I had easy countings from the first interval of 0 to pi over 2. Now I'm moving back pi over 3 and having to add pi over 2 every time. So I'm going to put these in sixths, right? So in this case, this is 3 pi over 6, and this is 2 pi over 6. So what I'll do here is I'll say, let's take that 0, and it's no longer there because I have a phase shift of pi over 3 back, or negative 2 pi over 6. And then I'm going to add pi over 2 intervals to that, which we know is 3 pi over 6. So add 3 to -2, I get pi over 6. I'm just going to label this as 4 pi over 6. You could reduce this if you want. 7 pi over 6. And 10 pi over 6. Now, the big thing you need to look for is that when you are done, you should have 2 pi in total from the start to the end. And from -2 to +10, that's 12 pi over 6, which is 2 pi. Sine graph again, no y changes. Just go ahead and graph a sine graph with the normal amplitudes of 1. Now notice in this example, we are outside of our sine function. This 2 is not in parentheses. If you go back to our original example and see what that looks like, you'll notice the following, that this looks exactly like the k in times of old, and that k was basically a translation up or down. So what this does is that essentially the k value is going to move your midline. So what we'll do here is say your midline is -2. Everything else is the same. Period is 2 pi, intervals pi over 2. So what I'll do is I'll take and draw a dotted line at -2. Notate that as my midline. And here's -1 and -3, and I'm putting this because I know my amplitude is still 1. Now, I will notate my intervals the same way as I used to. 0, pi over 2, pi, 3 pi over 2, and 2 pi. And you'll note that my x values are going to be the same, and so are my y's. The only thing that changes is I've slid everything down. So I start my 0, 0 here. I move over one interval, go up 1. Move over another interval, back to 0. Move over another interval, down 1 from the midline. And then back to the last interval of 2 pi. There's my sine graph. Looks exactly the same as a normal sine graph. Same intervals, same amplitudes from the midline. It's just been moved down. So now we're going to go backwards a little bit. We're going to write an equation of a cosine function having an amplitude of 7. That's pretty easy. 7 cosine. And then having a period of pi over 4. So if my period is pi over 4, that's going to be equal to 2 pi over k. And I'm going to need k to fit right before my theta value of y. So I go ahead and solve this, and I have 4 pi is equal to k pi, or pi k, divide by pi, and I get 4 is equal to my k value. So in this case, k is equal to 4. Here's my a, there's my k value, and I'm done. Do the same thing except in degrees now. We have an amplitude of 2, and we're looking for a sine function, so y equals 2 sine. And then I need my k value again in front of my theta, so the period, 540, equals, instead of 2 pi, I'm going to use degrees, 360 over k. So k in this case is equal to 360 over 540. The zeros go, and 9 goes into both of those. 4 times here, 6 times here, which means something else went into both of those, so I can go 2 and 3, and k value is 2/3. Finally, we're asked to write an equation of this graph, and they tell me it's a sine graph. I look at it, and it makes some sense. I notice that at 0, I have 0, except I notice instead of going up, this goes down. So I must be multiplying by a negative, first of all. So I'm going to do this, sine y equals a negative. And then I notice that I'm going from a midline to a height of 3. So I'm going to say -3 sine. And then I notice my period's changed. My period for sine is now pi. So my period is pi, which equals 2 pi over k. Therefore, k has to equal 2. And I'm done. And that'll do it for the day, and we will see you next time.